So chances are you're probably not the only ones having that type of a question. So I do have a review problem up here. I didn't realize there would be this issues, but we'll talk about that at another time. So what concerns do you have? We talked about number 10. You said,
Yeah, well, I didn't read it thoroughly.
oh, so it's changed since then?
Yeah.
Why is that?
Twice.
Okay, fair enough. Fair enough. Fair enough. Okay, so which one seems a little more confusing? Is it 3 or just go in order? All right. Okay. Make sure I got. All right, number 3. Is that where you have copper oxide and hydrogen? Is that correct? Okay. So there's different ways you can go about doing that. So let's get our equation up there first. Okay, so copper 2 oxide plus hydrogen. Okay, gives us our copper and water. Okay. All right. Then the next thing we want to do is look back at this and balance it, which looks like everything is balanced, correct? So part of the problem is even the workout that I've done on here, sometimes you're confined for space. There's nothing wrong with doing that on scratch paper. So what do you think would be easier? Because we've shown you 2 different ways to do this. One, you can pick one of your products out, and whichever reactant produces less of that product, that's your limiting reactant. Or you just stay on the left-hand side of the reaction. Compare what you have to what you need. Or maybe you don't know which one you'd want to see. Or would you rather just look at both of them? Both. Just one person wants to see both, too? Oh, okay. All right. All right. So notice that, again, we've got this balance. So the next thing is, if we got, 19.9 grams of this? Is that right? Okay. And we've got 2.02 grams of that. Okay. So let's just stay on the left-hand side of the equation first. So if you had tried to change both of these, see how much copper is produced, I mean, that's fine. Does anyone actually have the limiting reactant that they think? There's your limiting reactant. So let's show how or why that is. Now remember, don't look at that. I think the first mistake that could be made, oh geez, look at all that copper oxide we have. Hydrogen must be the limiting reactant. Well, really don't want to go by that. So again, we're staying only on the left-hand side. Okay. So what we would do is 19.90 grams. This copper oxide, we're going to change that to moles. Okay? So for every mole of copper oxide, we get, is it 79? $79.55. Okay. So these have canceled. Now that we've got that in moles, which is approximately about a quarter, would you agree? Now, okay, so I just want to put that down here to show you this is what we actually have. It's easier to see this if you're staying on this side of the equation when it's in moles. Okay, so we have 0.25 moles of that. There again, we're under that space constraint, if you want to call it, or you only have a limited amount. Okay, So now let's go ahead and change our hydrogen to moles. And again, my suggestion, or I should say our suggestion is don't just write it like that, right? It's just a good idea to carry that, no matter how heavy it is. Set it down because it's so heavy. Can't be. Hydrogen is the lightest element in the universe, so how can it be so heavy? We got to carry it. I'll keep going. Okay. So mole of H2, we get 2.02 grams of H2. So that gives us 1.00 moles of H2. So what that is saying is that's how much we have to spend. Okay? That's how much you have in that substance. Okay? So you have 25 cents worth of copper oxide. You've got $1 worth of hydrogen. Okay? So this is where, if you're staying on this side of the reaction, it's where we said it's kind of like you're playing Battleship. You shoot over here to see how much of that hydrogen is required. Same thing, shoot that over here to see how much copper oxide is required. Okay, we're past this step because what did we change that grams to? How did we get to a quarter? We already changed it to moles. Yes, you're correct. Okay, so we've got 25 cents worth and $1 worth. That's how much we have. So let's see how much is required now by playing this battleship and shooting them from one direction to the other. So in doing that, we change moles of copper oxide to moles of hydrogen. Typically, we would have to go back to our balanced reaction. There's no coefficients in there. Well, technically there is. So it's 1. Okay? So when we multiply this, how much hydrogen is required then when you multiply 0.25 times 1? 0.25. Okay, now I'm running out of space. Mole of H2. This is ReQ. We need 25 cents worth of hydrogen. Okay, how much did we originally have? Remember we said you have $1 worth. So we need to have 25 cents worth. So do we have enough hydrogen? Yes. Okay. So you might say, well, we've already proven what our limiting reaction is. Yes, that's true. But we'll keep on going so we really make sense of this. Okay. So we're going to take this mole of H2 and see how much we're actually short. So for every mole of C or copper oxide, 1 times 1 just gives you 1. This is ReQ. That's how much is required. So we need $1 worth. That's how much it costs. How much did we originally have? 25 cents. Okay? It costs $1, but we only had 25 cents to spend. Okay? That's one way you can determine the limiting reactant. Okay? We tried to explain that with every step that we went through. Okay? So, right middle. Are we good so far? And hopefully, yes, no, and maybe we don't know. Maybe we'd rather go the other way, which we'll show you in just a moment. Left middle. You're not left middle. You're just ahead of yourself. Left middle. Okay, left outside and right outside. Okay. So, again, these numbers tell us what we actually have. Okay? These numbers tell you what is required. Okay? And maybe that doesn't help. We just said that 3 times probably. What you have, what's required. Okay? So, that's one way to do it. Part A or Part B. We don't need to erase all of this. We can just erase this information. Because some of you maybe would rather see how much copper we're going to make. Okay? So again, we've determined our limiting reactant is copper oxide. So if we were to keep going, okay, and we can just change it to X amount of moles of this, okay? So, how do we get this mole of copper oxide to cancel? We're going to put it on the bottom, our next step. And then a mole of copper, because that's what we're looking for, X amount of moles, okay? So upon doing that, okay, looks to me like that's not going to change. It's still going to be 0.25 mole copper. Okay, so back to this. If we extend that out, okay, so for every mole of hydrogen, we get a mole of copper. That produces 1 mole of copper. But we already had predetermined that this was our limiting reactant. We did it by showing just staying on this side of the reaction or changing these grams to moles of one of these products. So the copper oxide produces 0.25 moles of copper. 2.02 grams of hydrogen produces 1 mole of copper. So since this produces less, go back to what we started with, copper oxide, limiting reactant, like we had just predetermined. So you can, and it probably does ask that, because it says, how many grams of copper are produced in question 3? Okay, so upon doing so, what you would do is, technically, can we erase this bottom one? We can. Why? Because this is our excess reactant. We have plenty of hydrogen. So we're going to get rid of this. Okay. And really, we're just taking that 0.25 times 63, right? What we mean by that is this. For every mole of copper, you get 63.55 grams of copper. So about 16 grams of copper. It's actually 15, so 0.88. Okay, yeah. We're hitting the dartboard, almost not quite hitting the, pretty close to the center bullseye. Okay. So, when you looked at that, have some of you decided, I just want to stay on the left-hand side of the equation? Some people may choose to do that. How many of you like the second way, where you're changing it to one of your products? Okay? You're going to have to do one or the other, and don't try to mix the two. Okay? So, again, it's kind of like a bad call. You're going to have to find a way to overcome that. Hopefully that makes sense, we hope. So, in just in and if you fall down with this, there's people around to help pick you up. This is difficult stuff. No one's gonna rebuke that or debate you with that. All right. Sure. Because and to finally make sense of again last night, if a lot of times what happens if people, I shouldn't say people, but teams double team you or double team Kenzie. You had other people pick up the slack. You had that balanced scoring. So should that be the case, you were limited on your success. Last night that wasn't the case. Okay. You said work on number 10. Well, it should be in grams because that's what you're going to take them off the periodic table with. Yep. Yes, and no one is arguing. You know, had to flip it over on the back side. Yours is double-sided paper, where I got two single-sided pieces of paper here. But does someone think they know what the limiting reactant is for number 10? You sure? It is N2O4. Is your limiting reactant. Okay, you have to find your limiting reactant first, then use that to find how much water is released. Yep. Okay, so, well, they give you the balanced chemical, maybe that doesn't help. Okay, so we've got 2 N2 H4 plus okay, now I think we got our reaction. So now whether, yeah, this was actually taken out of your textbook talking about the Apollo missions, which, as we know, 50 years ago, last July, is when you have those brave souls actually land on the moon. And sometimes it makes you wonder, do we actually have the drive? Do people actually want to go back to the moon? Yeah, I suppose. But wouldn't be for me. Sometimes I think, I don't even know if we have the technology to do that. And, what about the work ethic? Do we have the work ethic? Well, we hope so. But anyway, so what we need to do then is you can stay on the left-hand side of the reaction, and it just takes a little longer, that's all. Or you can take each one of these substances and convert it to one of those products. And say, well, let's just go ahead and change it to water, then we know how much is going to be released in the atmosphere. And I'd probably have a hard time arguing with that. But to get this started, let's see here. Okay, that's how many grams of that we have. Then okay, and then finally the last one is 4.5. Okay. You just want to go in order. Okay. So here again, we've predetermined that I had to double check myself. Supposedly this is our limiting reactant. So we'll go ahead and mark that out. Okay. So if we take, I'm going to use a color that we can see. All right. If we take, I should use the same color that's up here. Okay. Excuse me. So, how many grams of N2H4 do we have? $32? Okay, so 14 for every nitrogen times 2 is 28, plus 1.01 times 4 gives you 32.06 grams. Okay, so do we need to put a 2 here for this balanced reaction? No, we do not. Why not? It's not a mole to mole ratio yet. Okay. Now we need to go back to our balanced chemical reaction. This 2 goes down here. We got to put an 8 up here. Okay, so these are now gone. So for every 18 grams of water, we get a mole of water. So that would give you, obviously, a pretty large answer. No one would dispute that. Then, next, take our million grams. Okay, and does it say what it actually is? Dimethyl something. I believe it's called dimethyl sulfone, I believe. But we're just going to abbreviate that. That's why we got these color coded. So we know that we're referring to this compound. Because otherwise, writing all that information out, as long as you know what it stands for, you can do that. Okay. So when you add all them together, all them added together gives you what? 60.12. Right. Okay. next step, we need to cancel that out. So for every mole of dimethyl, I think I just would abbreviate it as DMS, I think. Okay. So 8 goes there. We've got a 1 here, so that's good. Then take this times 18. They're gone. Now we're in grams of water again. Okay, now we're really limited for space on the bottom. So 4.5, the most important one, because again we predetermined that to be our limiting reactant, N2O4. You can see that. Okay. So just like our previous 2 examples, for every mole of this N2O4, how many grams do we receive? It's in the 90s. Okay, yep, 92.02 grams. Okay. Now, how do we get this mole of N2O4 to cancel? Put it on the bottom. That's for every mole of water now. Okay, so what coefficients go where? That laptop's probably in the way. Okay, so just like all of these, 8's going to go on top from that number there. And what goes on the bottom? Okay, and then finally 18.02 for every mole of water. Okay, so let's perhaps divide and conquer. Can someone do the blue, please? Maybe someone has it already. And someone do the maroon or red or whatever color that is, and someone do the black colored, please. Okay, that's probably good. 2,698,371. Okay? 900 and what? 397. And then, okay. And whatever numbers these are, that's fine. So of these, which one's producing the least amount? The black one, which was what product, or yeah, what reactant that we started with, N2O4, and okay, we predetermined that was our limiting reactant. Okay. Okay. With when you find this one here, okay, it's asking you how much water is released. So then that's what your answer would be. 2 million. Oh, okay. So is it 2,000 kilograms then? 2,349 kilograms. That would be your answer for water. Yes. Okay. Now, I can't stress this enough. Some of you are going to be required to do this in 2 years. We want to separate the haves from the have-nots. We want you to be the haves, not the have-nots. Okay? Because we hopefully, when we take that pesky ACT test, we're hitting the high ends of the 20s. Okay? Who's taking? So, is anyone happy with their results? Okay. Are we going to take it again? Okay. Fair enough. Now, again, for those of you who see this in 2 years from now, the better you're at, it's going to open more doors for you in college. Okay? We stress this for a reason, I hope. Those good old logical thinking skills. All right. We have a shortened period tomorrow. So we've already moved everything to the right one day. We'll start with this here tomorrow then. Is this enough for today? Is your head spinning? Because if it is, isn't that what happens in The Exorcist? Child's head spins all the way around. You're going to have to do an exorcism on him, maybe. No? No? All right. We'll catch up to you next time.